Okay, so let's imagine that we have a circle, or rather an object that's moving on a circle because it's attached to a string. So here's an object of mass m, and it's moving on a circle with constant speed v naught because it's being held by a string that goes through. So this could be a horizontal surface. It's a table. This is sort of a classic example. There's a hole, small hole at the center of the table, and the string can be pulled, so it can be made shorter. So initially, the object is going around at constant speed v naught, and the length, let's say, is L. And then later, you pull the string such that, say, it's going on a different circle, maybe a third of the length. So that's L over 3. So you pull this object, you pull the strings slowly so that the object continues to move on a circle, ever smaller circles, until the radius is L over 3. And let's say we want the final kinetic energy of this object. So there's some intuition here that there's some work being done because the object is moving also in the direction, right? It's going on ever smaller circles, but it therefore is moving inward, so it is moving in the direction of the force. There should be some non-zero work. The object should speed up. But it's also true that the force isn't producing a torque about this point, so the angular momentum about this point needs to be conserved. So those two principles need to be satisfied. So if we think in terms of work and difference in kinetic energy, then the final kinetic energy is the work plus the initial kinetic energy, right? Because work equals delta K. And so that's the work plus m v naught squared over 2. And so we need to find the work. So let's calculate the work. Right, that's the integral of the force. We have to figure out the force, which is the tension in the string, F dot dr. We're going this way from L to L over 3. So we're going to smaller values of the radius, and we need to figure out what F is. In magnitude, it's just MA equals F, and F is the tension force. We can figure out what F must be from the left-hand side, the MA side, for circular motion, which is just mv squared over 2. But this way is negative, smaller values of radius. We're moving in the negative direction. We're pulling in towards smaller values of the radius. So this looks like we will be integrating a quantity, which is mv squared over r, in dr from L to L over 3. And now we have to figure out the dependence on r of v, and that requires the other principle, which is constant angular momentum about this point, because there's no torque about that point. And so the angular momentum, which initially is m v naught L, has to be the same at all radii, so it's m times v times r, and so we can conclude that v is equal to v naught L over whatever the r value is. And so we'll plug it into this, and we'll get a minus m v naught squared. That's a constant. L squared is also a constant. We end up integrating from L to L over 3 in dr over, we squared this, and there's an r already there, so we get an r cubed. And so we get a minus m v naught squared L squared times minus 1 over 2r squared. That's the result of the integral of 1 over r cubed from L to L cubed. And that is minus m v naught squared L squared times minus 8 over 2L squared, which is 4m v naught squared. And so the final kinetic energy is going to be that plus, so that's 4m v naught squared plus the initial, which is mv naught squared over 2, and that is 9/2 mv naught squared. So the kinetic energy has increased. We've done positive work. A more straightforward way is to just think about kinetic energy in terms of rotational quantities. In this case, we have 1/2 the moment of inertia of a point particle, just mass times distance squared. So the final distance from the center is L over 3. We square that for the moment of inertia. And then the angular speed is just a linear speed over the length. So omega is V over R. And that is from up here, we see that that's V naught L over 3. Over 3 squared, which is 9 V naught over L. And so we'll do 9 V naught over L squared. And that, of course, gives us the same final kinetic energy.